Hello, everybody. Welcome back. In this lesson, we will go over two important concepts. The first one, the definite integral. The second part will be the fundamental theorem of calculus. So first of all, let's consider the integral. When we consider the, the theory of integration, the process of integration, there are two main branches. The first one is indefinite integral that we are already familiar with. In other words, this is exactly the computation of the antiderivative. So we know by practice this is computational. On the other hand, the other branch, by definition, the definite integral is geometric. So what do we mean by the definite integral, the definition of the definite integral being geometric? The way that we define the definite integral is like this. We consider a graph, let's say a graph of a function. To consider a definite integral, we need to have two values, a and b. These two values are located on the x-axis. And the role of the definite integral, first of all, let me provide you with the notation, a to b, right? So it is pretty much like similar notation that we had for the indefinite integral. So it's from a to b, and then we have f of x dx with the integral sign. So the only difference is having these two bounds um, other than what we had in the notation of indefinite integral. So however, now this notation is pretty close to what we have seen here. However, what is the meaning of this? The way that we define this quantity, this new quantity, is none other than the area under the graph of the function. Or more precisely, you can say it is the net area under the graph of the function, or the net area between the graph and the x-axis. Given that if there are any portions of the graph going below the x-axis, then you will consider them as a subtraction other than an addition. So you will consider the net sum. So we can have those technical details later. Now, when you consider this geometric quantity, now one can naturally ask this question. Why do we have indefinite integral and definite integral? Those two are sharing one common technical term, integral, and those two by notation also very much like familiar. Why do we do this? These two are coming from way two different perspective, one being computational, the other one being geometric, but yet why do we have such similarity in these two components? The reason is these two are related to each other. How related are they? They are related in a way that these two can be linked with each other. And we will see that component, that particular part in a moment. But this connection, the link between these two is what we call the fundamental theorem of calculus. And more precisely, we consider the part one of the fundamental theorem of calculus. There will be two parts, and we will cover both of them in this lesson. And with this, we will see both of those directions in consideration. And the important aspect is now, first of all, since we defined the definite integral for the first time in our description as a geometric quantity, now let's try to answer a couple of examples. Let's try to look at a few examples. Let's say I would like to compute this 0 to, okay, let's say 1 to 2. The function is x, and of course dx is supposed to mean the measure of the integral. In other words, integrate the function y equals x from 1 to 2. That is the challenge. Now, how would you do this? Now here I provided the answer also. I have the answer written form in the written form, and I will reveal it one step at a time because it's so simple. It is not an example. In fact, it is like an example zero, just an illustration. If you draw the graph of this function, look at this. The graph of the function is none other than just y equals x. And we know from 1 to 2, that means on x-axis, we do have these two pieces, 1, starting from 1 all the way up to 2. Now, if you consider the corresponding y coordinates, one can easily see what's happening with the y coordinates. The y coordinates are going to be respectively the same, y equals 1 and y equals 2. Now, since we mentioned that we consider the area under this graph, right? So we are looking at the area right here, area between the x-axis and the function. So the question is now, why don't we just compute it geometrically? We can do that. If you think about like this geometry, you can clearly see here we have a square. Look at this. It's just the base is 1 and the height is 1. It's a square. So we know the area, it's going to be just 1 times 1. On the other hand, when you consider what's lying on top of that is none other than a triangle. That triangle has again base 1 and the height of the triangle is 1, and we know the area of a triangle. That would be 1/2 times the base times the height. So if you do that, you can clearly see this is corresponding to the triangle, the area of the triangle, and this square is right here, the area of the square. Now, if you do the computation, one can see it is none other than 3/2. Easy computation completed. And that's how you can get this answer. Now, yes, the idea is pretty much like this geometric definition is wonderful. You can work it out. But now, this is the caveat. Think about a very simple extension of this problem. Consider just a simple, very simple extension. Other than having x here, we are going to have x square. Once you have it, what you can see is now if you try to draw the graph of this function, you're going to get something like this. We know it's a parabola, y equals x square. Now, if you try to do this process from 1 to 2, right, you will see 1 corresponds to 1 because you square 1 and you're going to get just 1. And then when you square 2, you're going to end up getting 4. And now if you look at this very carefully, if you try to go ahead with what you did earlier you had a square, and on top of the square, you had a triangle, a perfect triangle. Now, yet you have a regular geometric shape right here, which happens to be a square, even though it doesn't look like a square in my context, in my drawing. This is a square, that is good. So it's not a troublemaker. However, if you consider what's on top of that, this piece, it is not a triangle. Can you see there's a curvature on this component on the along the graph? So if you try to compute the area of that region, which is exactly between uh, that almost like a curved triangular kind of a shape, right? That under the parabola. If you try to do that, it is not going to be a precise computation because of the curvature of the function. So with this, you can see whenever we have a nonlinear function, when nonlinearity is involved in the situation, this is not going to be a very good definition to work with. Or in other words, you cannot do this computation directly. So in this question, in this example, example number 2, This is an example where I'm going to say, in fact, I cannot answer. I'm still puzzled, and I'm going to say there is no answer that I can provide right now. So that's what I can say by the definition. Now, this is exactly where the connection between the definite and indefinite integral, in other words, the most powerful tool that you see in calculus, the fundamental theorem, comes to play. So what is the role of the fundamental theorem? Let's look at the first part of the fundamental theorem of calculus. The first part of the fundamental theorem of calculus states something like this. First of all, you need to compute a definite integral. Now the question is how you can do that computationally. You need to find a computational way other than employing this geometric way that would be really confusing in nonlinear functions. Right? So what can you do? The fundamental theorem, first of all, let's go back and recall the word theorem. What do we mean by a theorem? A theorem is a mathematically significant true statement that has a proof. So it is a true statement at the same time it has a proof, and that kind of a statement is recorded in mathematics, and uh, as far as they are applicable in a variety of domains, they have recognition. So this is one such theorem which has enormous recognition, not only in calculus, but also beyond that in the application layer. But now, what does it say? It says simply, when you need to compute the definite integral, you can simply employ the antiderivative. In other words, when you say you're going to employ the antiderivative, don't forget the antiderivative is just none other than the indefinite integral, if you recall what it is. Do you recall the notation? The indefinite integral is simply about finding the reverse of the derivative to come up with the antiderivative. So antiderivative simply means the just the reverse. And let me just put it here, indefinite integral. So other than saying antiderivative, one can say it is none other than the indefinite integral. So once you have the indefinite integral, what you can do is to compute fb minus fa, where this uppercase f is playing the role of the antiderivative. So antiderivative evaluated at the top bound, b is the top bound, and the antiderivative, and then minus the antiderivative evaluated at the bottom bound. So that's what happens in this context. So the method is mentioned here. First, compute the indefinite integral, step 1. So when you have bounds, do not panic. The first step you're going to do is to pretend that these two bounds are not in the context and compute the indefinite integral. And then once you have the answer on your hand, you're going to compute fb minus fa. Let me show you an easy example. Example number 1 in this context. Let's take the integral of integral or the definite integral given here. How do we compute? The first step, we are going to pretend that we do not have these bounds. So in other words, I'm going to just delete them for a moment, and that is what we have here. So I'm going to compute the indefinite integral. And when I do that, all right, so this is what I get. X squared will result x cubed over 3, and then minus 3x squared over 2. 5 5 will result after the integration. It's 5 times x, and then do not forget the plus c that you're going to end up getting at the end. With all of this, now the next step that we're going to have is to compute. Now this is, don't forget, this is uppercase f of x, your antiderivative. So then the next step, to include these two bounds from 1 to 2, all you need to do is to compute f2 minus fa from this uppercase F found in this step. So let's do that computation. And when you do that, what do you get? Uppercase F is just exactly what you see here. So let me just transfer it to the next step. And I'm going to plug x equals 2 in that expression. So this is what I get. Do not forget plus c is in the context state. So I will just leave it there and then minus. And then I will plug x equals 1 because that's the input value here, x equals 1 in the same function. This is what I'm going to end up getting. Now, do not forget I have minus in between. And can you see what happens to plus c in this scenario? Here you have plus c. Here with this minus sign, this plus c becomes minus. So plus c will get cancelled with that minus c, leaving that arbitrary constant out of this context. So in other words, for every definite integral, you're going to see this. You will never have a plus c in definite integration. When you have a definite integral problem, your final answer will be just a number, just like what you see here. The final simplification will lead to just a number and there is no plus c. And that's why it is called a definite integral. There is no indefiniteness in that answer. There is no ambiguity involved with the plus c or an arbitrary constant. So from this point, let's look at another example to see. All right, so let's look at this right away. Here, the starting value, the lower bound is 0. It seems like a 6 because of my handwriting, but it is supposed to be 0. Now, let's integrate this. First of all, you're going to find the integral. Now, in computations, you can do this without just ignoring these two bounds right away. You can just delete them and take the indefinite integral and then you can proceed. Or you can do this. You can just simply pretend that, have them in your notation here, but pretend that it's not there and just write down the answer for this indefinite integral. Pretend like this is an indefinite integral problem. So just find the integral. When you do that, you know the integral of sine x is going to be negative cosine x. Therefore, with this constant multiple, it will turn out to be just negative 2 cosine x. And then 3, it's a constant. When you integrate, it becomes 3 times x. So now this is what you have. And then after having that answer, let me use a different color here. After having the answer, I will put brackets around and then I will indicate these two bounds here, 0 to pi over 3. That is the bound, the top bound that we have. The meaning of this new symbol, what you see in the right-hand side of this computation is a new symbol. What is the purpose of this new symbol? It is kind of a placeholder until we do the computation. This is none other than our f of x. Now, don't forget, the role of plus c of the antiderivative is meaningless in this case. So that's why I did not include plus c in this answer. I just got the kernel of that answer. And then what I'm going to do is to plug in the bounds in the next step. Where should I plug it in? I should plug it in the antiderivative. So I will just plug it in this function wherever you see x. And this is what you're going to get. Plug x in there and you will get the first component and then minus and then the second component where x equals 0. When you plug in x equals 0, you're going to end up getting just cosine 0 in the first place and then 3 times 0. Of course, the second component will disappear. And now here comes some computations. Pi over 3, in other words, 60-degree angle. Now you should recall the unit circle in this scenario, right? By any chance, if you do not recall the answer for some reason yet, in calculus viewpoint, it makes sense to leave the answer like cosine pi over 3. However, it is the common knowledge that you need to have. Now, at this point, if you do not recall the basic trigonometric ratios, I recommend you to go ahead and check the unit circle just for the basic trigonometric ratios. So cosine pi over 3 is none other than 1/2. That's what we have here. Don't forget, 1/2 will cancel with 2 that appeared in the previous step. And then here 3 times pi over 3, because once you have just x, just include x. So 3 times pi over 3, again 3 will get cancelled, leaving a nice round notation, symbol at least. And then minus makes it plus, which you see here, and cosine 0 happens to be just 1. Cosine 0 is 1. Therefore, you have the answer turn out to be just pi plus minus 1 plus 2. So simplify, it will turn out to be 1 plus pi. So it is just the same practice. As far as you know how to compute the antiderivative, you know how to get the answer for a definite integral now, thankful to the fundamental theorem of calculus. Let's proceed to another example, which is supposed to be an easy one, right? Because you know the integral of secant square. 3 is a constant factor. You can bring it out and integrate secant square, which is none other than just tangent, plain tangent x. When you have it, now plug in these two bounds and see if you can figure it out. Give it a try. I hope you gave it a try. And now, once you have the answer, 3 tangent x, after the integration process, now you're going to plug in pi over 6 in this, and then minus pi over minus tangent of negative pi over 6. And tangent is an odd function. In other words, when you have a negative sign, you can bring it out, or simply you can check that on the unit circle to get the value. But in this case, I use the trigonometric properties to move this negative sign out of tangent to make it plus here. And then 6 tangent pi over 6. That's our answer. However, you can simplify this if you recall the value of tangent pi over 6. Tangent pi over 6, in other words, pi over 6 is a 30-degree angle, and that results 1 over square root of 3 for the tangent. Or in other words, it can be rationalized to square root of 3 divided by 3. However, this particular part is nothing about calculus. It is about algebra or trigonometry background that you need to recall. The calculus ends right here. Let's proceed to the next step. In the next step, we will look at a few properties of the definite integral. Now, being a geometric quantity, the definite integral has an amazing collection of geometric properties. Some of them you can verify geometrically, some of them can be verified algebraically. First of all, if you have to integrate a function from starting from a all the way up to a value called c, let's say in between a and c, you thought about having a break. Let's say you started integrating from a all the way up to b and then had a stop at b, and then again you started from b to c. Now, if you do this process, the area from a to c is same as the area or the definite integral from a to b plus the definite integral from b to c. Why does this work? If you look at this picture, it can verify simply uh, what's happening in this scenario. When you consider a to b, now this is the graph of the function y equals f of x. First of all, when you consider the first interval from a to b, you're considering this interval, and the area that you're considering is right on top of that. It's that picture. And then similarly, when you consider the second part, b to c, it's none other than the area under this function from b to c. That's exactly what's indicated by this blue region, and that gives us exactly the second component. Now when you put them together, what do you have? When you put these two pieces together, you can see exact picture of the graph from, let's have a different color to emphasize this fact. You can clearly see this entire region. Why don't we highlight it? This entire region, because it's the area of the function starting from a all the way up to c. That's exactly what you see on this, in this part. Therefore, that's exactly how you can see this nice result. And apart from that, you can verify the same idea computationally. If you look at it computationally, just considering the antiderivative and considering fb minus fa, in this computation you can see the term evaluation of b will get cancelled because it appears in two different locations, one being plus, the other one being minus. Second property, property number 2. This is obvious. If you integrate, and if you start from a point and if you end up with the same point, then your integral will result no area at all. So that simply means the integration will result just a 0. Why does this happen? In this scenario, the length of the base, usually these values that you see on the x-axis would indicate the length of the base. So when you consider the base in this scenario, it's none other than just one single point. There is no length associated with that. So on top of that, you cannot define an area. So it's going to be just, you can define an area that would be just 0. It's a trivial result. And then the next step, property number 3, by any chance, if you think about like switching the bounds of an integral from a to b, you have an integral from a to b, and you would like to switch the bounds due to some reason. I will give you a couple of examples for valid reasons for this. And if you switch the bounds, this is how it would work. If you switch the bounds, now here I have a at the bottom, b at the top. When I switch the bounds, b at the bottom, a at the top, and the compensation will be having a negative sign in front of the switched integral. Why does this work? Think about this. If you computed this, you're going to get fb minus fa, right? That's a fundamental theorem. However, if you computed this one, you're going to get just this integral itself without having the negative sign. If you just concentrate on this piece, you're going to get f a minus fb instead, because the top bound is a. And then what is the difference between these two quantities? Those two are almost the same except for one negative factor. If you multiply it by negative sign, the first term becomes negative, the second one becomes positive, making it equal to each other. So that is a simple way to look at that property. And then, in addition, we do have linearity properties. What are linearity properties? We have seen them already in the context of indefinite integral. when you have an addition or subtraction of functions, you can simply integrate it separately. In other words, you can distribute the integration operation over uh, any addition or subtraction. On the other hand, when you have a constant multiple in front of a function, you can bring the constant multiple out of the integral operation, um, and then integrate only the meaningful function component of that composition. And then these two results together is what we call linearity properties. So in other words, the integral operator is a linear operator. Let's look at an example. Let's pretend that you have a function, one single function. Read this and note it down as necessary. But this one is a conceptual problem because this function f of x is not given in the context. So what we have is one function, and first of all, the integral from 0 to 3, and then from 3 to 6. And these two values are given, the final values are given. And then we are asked to compute a couple of things. Compute the integral from 0 to 6. That's the first one. 0 to 6, the integral of 0 to 6 is none other than the integral from 0 to 3 plus 3 to 6. Right here, I'm being just lazy without writing fx dx in both of those cases, but it is supposed to be the complete notation. However, the integral of these two, these two are none other than these two pieces. So 4 plus minus 1 equals, that's just 3. And at the same time, one should ask, like, can an area be a negative value? Because we are considering uh, an area under a given function. Yes, that is exactly what I called what I mentioned right at the beginning. When you consider the definite integral, it is not just the area, it is the net area. So if there is a portion of the function below the x-axis, that would result in negative addition to that component. So uh, as a matter of fact, it can become, a definite integral can become a negative. And then when you consider the next component, part B, what is 6 to 3, integral from 6 to 3? Now 3 to 6 is given. So if we have 6 to 3, if we switch the bounds, it is none other than just negative of 3 to 6. So that is supposed to be negative and times negative 1, which is already coming from this. So it's going to be just positive 1. The next part, from 3 to 3, nobody needs to say anything about this. The same bound. So we know what's going to happen. It's going to be just 0 because there is no length in the base. And then the next part, what is the area? What is the answer for 3 to 6 negative 5 times fx dx? To answer this, don't forget, we can employ linearity properties. This constant multiple can be brought out. If we do that, we end up getting negative 5 times 3 to 6 fx dx, but this component is already containing an answer, right? 3 to 6 is none other than just negative 1. So let's put it in that position. So you have negative 5 times negative 1 equals just 5. And then let's look at another similar example. Similar in a certain way, but when you look at this context, you can see functions are different. F and g, two different functions. However, the bounds are the same. Now, if you look at this carefully, you can see this is none other than the linearity properties. That's exactly what we should expect. Let's look at it. What is the integral of the same over the same interval f of x plus g of x? The answer is pretty simple. That is the addition of these two components, because we can integrate these two separately. So integral of f plus integral of g, right? So this component is exactly what we say. It's plus 10 plus minus 2, and then it's just 8. And then in the second component, you will end up getting 5 times the integral of f, right? So by linear properties, you can just do this. 2 to 6 f minus 7 times 2 to 6 g. And we know the answer for each component. This component is none other than 10 minus the second component here is none other than negative 2. Now simplify. The first one results 50. The second one results positive 14 due to negative negative making a positive. So altogether it's 64. So it is that simple, employing these properties in a conceptual problem like this. No big deal. All right. Now let's look at more computations. First of all, this concept, now the notion of definite integral, that can be used in any kind of a integration problem. So for instance, this is a typical problem. This is an example where you can actually employ a u sub, because there is no way that you can integrate this on right away because that has a fraction. But if you employ just this denominator as a u sub, you end up getting the derivative ex dx, right? So this component becomes just du, and 2 is an innocent constant that you can bring out, and then that's exactly what happens here. You end up getting du, and then 2 brought out here, right? And then you need to integrate this, and when you integrate it, you end up getting this. Finally, ln u. Now you can plug it in back. U is none other than ex plus 10. Now once you get to this point, what you can do is to get this component, don't forget the practice, right? Once we have the antiderivative, we're going to just compute the definite integral employing that fb minus fa. So just compute from 1 to 3 that value. So once you plug in x equals 3, you're going to get e to the thirds plus 10, and then minus 2. It's just the constant multiple that you see in front of both of these pieces. That is generic. And then when you plug x equals 1, you're going to get ln e plus 10. So that's the final answer. There are different varieties that you can produce as the final answer. You can simplify it in different ways, but this is the answer. Simplifications could be, simplifications will be just algebra beyond that. All right. So another problem. Now find the area bounded by the graphs of y equals x squared plus 1, x equals 0, x equals 3, and y equals 0. Now let's put all of them in one single picture so that we can see. Y equals x squared plus 1. It is none other than just a parabola, and it starts at 1. So that's exactly what we see. At 0, it's going to be 1, and then it curves up. And then x equals 0 and x equals 3 are vertical lines that you see here. Let me just draw them in red color. So this is 1, x equals 0, and it goes all the way up. But I do not need to draw the whole thing, because it's just about this region that we need to be concerned about. So x equals 0 and x equals 3. And then y equals 0 is none other than the x-axis. So I will have it exactly in blue color right here. The blue color line is y equals 0. So what is the area trapped between all of these pieces? It's none other than, when you look at it carefully, when you put it to the graph, you can see it's the area under this graph from x equals 0 to x equals 3. So just integrate it from x equals 3 to 0 to 3. Integral, not a challenge. Then plugging values, in other words, knowing the fundamental theorem is the key. And then when you plug 0 in the position of x, you can see it disappears. There is no contribution from the lower bound. So you're going to get whatever you get with the top bound. And that's what you have here. All right, let's ponder. Now, what did you really do? What is the real process? Of course, we do understand this process, but it's a computation. But what is the underlying uh, significance of this entire computation? Now, this is none other than the interconnection between derivative and the integral. That is what we explored, if you didn't see it in that way. Now, why do I say that? Now, pretend that you have a derivative. If you have f prime, its antiderivative is none other than the original function itself. F prime, and if you integrate f prime, what you're going to get is just original x, original f of x. So when you have the derivative in an integral, right, when the derivative and integral are together, the essential action that you had at the end is the recovery of the original function. Look at this. This is just the original f of x. So more clearly, in concise words, if you just look at it like this, if you have the integral, okay, so integral followed by the derivative operation. First of all, you have the derivative of a function, and then you take the integral. When you have these two pieces together, those two will conflict with each other, those two will fight with each other, and then will disappear, leaving just function f of x alone. But there is an underlying situation, underlying condition that you need to pay attention to. You're on a certain playground, that is exactly the interval. So it's going to be fx, not just fx, it is just fb minus fa. So in simple words, when you have the derivative and the integral together, those two are mutually inverse to each other, but they, in this case, we considered a very specific order. First, we have the derivative, then we have the integral. We have the derivative inside and then the integral. Now, if you consider other implications, one other implication, other meaningful question that you can ask is this. What if I have the derivative and I have the integral first? I have the derivative, I have the integral of a function first, and then I take the derivative of whatever that answer. What would it give us? Because if this is going to work, then it doesn't really matter which order you're going to put these two operations, the derivative and the integral, they will always act as inverses to each other. That is an amazing result because you can just interact them to recover the original function. Now, does this work? In fact, it does. That is the second part of this amazing theorem, of the fundamental theorem of calculus. So the second part of the fundamental theorem of calculus says, if you take the derivative, now the only technical detail that you need to, there are a couple of technical information that we need to work out. You cannot simply say, like, without having uh, bounds, it doesn't become precise in computation. So here you have a constant bound at the bottom and a variable bound at the top. And this variable bound, these two are matching perfectly with each other. Look at this. The variable of the derivative, variable of the differentiation, variable of the differentiation appears here, exactly is the same quantity as the top bound of the integral, and a is none other than a constant. It's just a value, a fixed value. And in the meantime, inside the integral, do you see I did not employ fx dx? In other words, I did not employ variable x to write down the interior. Why? Because we already used this as a bound. Now, if we override the same variable, variable override is a catastrophic scenario in mathematics in most cases. So that's why this is just a dummy variable. T is playing the role of a dummy variable in this computation. So it doesn't really matter. It could be anything other than x. Now, this is the recipe. If you have x here, if you have x there, and the derivative is just followed by the integral, the derivative will fight with the integral to recover the original function. But the original function is not going to be f of t, because think about it. This whole thing is supposed to be, after the computation, it is supposed to be a function of x, because it's going to be something of the form of x fx minus fa, right? If you compute it precisely. This is a function of x, and now you differentiate it with respect to x. Can you end up getting a function of t as the answer? No, it's not possible. So there is no meaningful variable t outside of this integral. So what you're going to get is a function of x. So that function of x is none other than just the original function itself. And of course, it's a function of x. So the inner variable is going to be x. So let's summarize this. The summary is none other than just, if you have this recipe, a fixed bottom number in the integral and x at the top, or the same thing here, the variable of the derivative right appeared here, these two. Then what you're going to write here is just the original function with the same variable that you see in this agreement. So let's play with an example and see what this means. All right, there's a little bit of a void in the document. All right, so let's try to see what we have here. Now, in this case, look at this. You can now, by any chance, if you do not recall this result, or if you just skip this lesson, that simply means you have no clue that there was this kind of a lesson. But yet, if you're familiar with the integration and differentiation, you can answer this, because you can find the answer for this parenthesis. Inside the parenthesis, it's simply integrate cosine. You know the integral of cosine is going to be just sine, right? And then when you plug in values, you will end up getting sine x minus sine 0. That will turn out to be just sine x, because sine 0 is going to be 0. And that differentiate, when you differentiate, you will get just cosine x. That works. So the answer is cosine x. But if you follow the second part of the fundamental theorem, once you see this derivative right after the integral, and this is a fixed number that you're seeing right here, and this is just the same x as that, what you're going to do is just to copy this function without t, and then just replace that input variable by x. Now, why is it necessary not to do that simplification and to use the fundamental theorem? It is just what you see here in the second example. Now, in the second example, you can actually, in fact, you can do the integral. If you employ a u sub, you can do that. Think about it. But other than doing this integration first and doing this derivative just to see, it did nothing, because these two operations will conflict with each other, they will battle with each other, and then they will vanish. If that is the case, if you knew that fact, you can write down the answer. What is the answer? Here you have the same variable in the agreement, and this is a fixed value. Always check the recipe. And then you're going to write this function in terms of x. So the answer is going to be x cubed divided by x to the 4 plus 5. It's that simple. No justification is needed in this case, because the justification is hidden behind the fundamental theorem of calculus, and this is a result that is worth knowing. So that's why you get the credit only for knowing this fact. The next example is a perfect example for why this is really needed. In example number 2, by employing a u sub, you could just do this without using the fundamental theorem. So simply you can bypass the fundamental theorem in example number 1 and example number 2. However, if you try to do it here, you're going to get into a huge trap. Because this is a function, honestly, I have no clue how to integrate. Even I do not know how to integrate this one because I randomly wrote it. Integration as a process is a very complicated, very tedious, because it's an inverse process, inverse operation. So I do not have any hope in integrating this function. Instead, what I'm going to do is to employ the fact that these two will conflict with each other, those two will battle with each other, and just annihilate, leaving this function as a result. So check the recipe. We have the same variable in these two locations. Why do I emphasize that fact? Soon enough, you will see the situations where we do not have the same function in both locations, but in this case, it does. And then apart from that, the next component is fixed lower bound. And then once you have it, I'm going to just copy and paste this function with the variable x. So I'm going to do just with the square root x cubed plus sine cubed x plus 1 divided by e to the x ln squared x plus 5. That is my answer. Just knowing that these two will conflict with each other, that's all you need to know. All right. The next example, an extension. Now, this is a situation where we have a fixed bound, lower bound, and the derivative and an integral, perfect recipe for this conflict, the battle between the derivative and the integral. However, there is something off from the recipe, because look at this. Here, x, at this place it's x, at this place it's x square. So there's a mismatch. How are you going to deal with this scenario? If you paid attention to differentiation up to this point, if you give this a little thought at this point, you can recognize the answer. I can give you the keyword. It is just a chain rule. If you'd like to take a look at it, and if you'd like to accept the challenge, at this point, pause the video and give it a try. I hope you gave it a thought. It's okay if you got stuck in that problem. Now let me show you what I'm going to do to fix this issue with these two, the mismatch of these two places, which was essential in the computation, right? In the second part of the fundamental theorem. So what I'm going to do is to write this one like y equals x square. I'm going to write y equals right in front of the top bound. And then I will write it separately, y equals x square. Now, don't forget when you, if you consider the integral of this, now what you're going to get is a function of y. You can differentiate it with respect to y. You can do with respect to y because it's a function of y. T cubed sine t. However, now it's not the same. Even if I write equals here, it is not the same because here you had x, here you have y. So it is not the same anymore. So to balance this, what should I have? This is none other than the chain rule. So in the chain rule, what we have is the interior function or the inner function of this computation differentiated at the end. So dy dx. Or in other words, if you do not recall exactly this form, this what we used here, what we employed here is this form of the chain rule, dz dx equals dz dy dy dx. What you see right here in these two pieces are respectively what's appeared on top. So this component is the first one, and this one is the second one. Now with this, what do we have? Now differentiate this, what we're going to get is the same variable, therefore the same variable. Now it's the fundamental theorem just in the regular form, but don't forget it would be just y, not x, right? So we're going to have this function written in terms of y. So y cubed sine y times dy dx. Now, do you see the reason why I wrote this y equals x squared separately? Because now, if you consider dy dx, if you take the derivative, let's write it carefully, dy dx, the derivative is none other than just 2x, and that's what you have here. So let's multiply just 2x. Now the final answer. Of course, we introduce this variable y into this picture, right? So do not provide the answer in terms of that variable. Let's switch it back to the original variable saying y is x squared. So x squared to the third, it's going to be x to the sixth. If you would like to simplify, even if you do not simplify, I wouldn't mind because it's a cosmetic matter. X squared times 2x. Let's work with one more example, and in this case, I will just do it a little quicker. Now, if you'd like to challenge yourself, or even if you don't like to challenge yourself at this point. Pause the video and give it a try based on what you've seen in the previous problem. So now, I hope you gave it a try, right? If you got the answer, that's perfect. You can simply proceed to the next problem. Or let's say, if you didn't get it, if you have any confusions, or if you'd like to check your answer due to some confusions, let's do it. I'm going to write y equals, or even if you do not write y equals, you can do it simply like this. First of all, in the first step, replace this top function, replace this variable given in this function. Now, in this case, it's not t, it is r. It could be anything. Replace r by sine x simply. So it's going to be sine cubed x 2 times e to the sine squared x times. Now in the next step, don't forget you need to take the derivative of the top bound, which is just exactly the variable change if you had a substitution y equals sine x. So that's going to be the derivative of sine x, that's going to be just cosine x. So the final step is none other than just that uh, derivative in the computation. All right, so let's proceed to one more example. And now, before proceeding, look at this example and think about it for a moment, because you have all the tools in your toolbox. All you need to do is to recognize how to use them in the scenario. Take a moment and try to work with it. All right. I hope you gave it a thought. And now, what can we do? Now, this is exactly where you can employ properties of definite integral. Usually, we need to have in our recipe book, we need to have the fixed bound at the bottom, the variable bound at the top, but we are not seeing it right here. So what can we do? We can switch the bounds by extracting a negative sign out. That is one of the properties that we had in our definite integral property list. So now, don't forget, when you have a constant multiple inside a derivative, you can bring it out. So negative comes out, and then the derivative of 5 to x squared plus 1 sine t dt. Again, don't get to this trap, because here, look at this. Sine t is an easy enough function that you can integrate and then you can differentiate, but that would be a time waste unless you know the fundamental theorem. If you do not know the fundamental theorem, of course it's going to be a time waste. If you know the fundamental theorem, you can save some time with that process. So now, first of all, simply plug in whatever is bound in the position of t. So it's going to be sine x squared plus 1, and then times. Then what you need to have is the derivative of that top bound. So that is going to be just 2x. And based on this, like you can use, I mean, it's not limited to this changing of bounds. It could be any other property in the in the uh, definite integral property list that you can employ in these computations. All right, so with this, actually, we come to the conclusion of this lesson. And make sure to have some practice problems. And of course, in this case, the computations were not heavy, but it was extensive because we had the fundamental theorem. We talked about the definite integral and properties. All of these are key components that you need to have to be familiar with this interplay of the derivative and the integral. So I hope you you will have a really good practice, because this is a takeaway from this course to the next level. All right. I will see you in the next lesson. And until then, enjoy problem solving and understanding mathematics uh, clearly. Have a wonderful time.